From the Model menu, General Settings. Define the general characteristics of the model, name, type of building, structural codes. Then define the location of the intervention, the structure type, the soil category, and the automatic definition of the limit states and capacity criteria. Model Geometry settings, from where you can manage and define the dimensions of each floor of the building, in order to define the corresponding levels or elevations. Create a new level, assign the elevation, define it as seismic or non-seismic. If the level is non-seismic, no masses are associated to that level, non-seismic, and all the masses at that elevation will be transferred to the upper level. In addition, for non-seismic levels, no control points are assumed during pushover analysis in the controlled displacement phase. Elevations to which no significant amount of mass is associated can be defined as non-seismic, for example, elevations at stair landings, elevations on parapets at the top of buildings, etc. At elevation at the top, seismic elevation, those associated with a significant amount of mass, usually for example at the floor levels. Define materials, masonry materials. In the left list, enter the name of the material, and in the right window define the masonry type, the knowledge level, and the mechanical properties of the material. Define sections, slab sections. We can define here the slab type and the geometric characteristics of its section, from which the parameters of an orthotropic slab, equivalent to the intended slab, are automatically obtained. Select the slab type from the predefined ones: ribbed concrete slab, solid slab, timber slab, timber concrete slab, slabs or vaults between girders. Finally, by selecting the custom type, you can modify the mechanical characteristics associated with any intended flexible slab type. Next, assign the direct elasticity modulus in the two main directions of the slab, Ex and Ey. The tangential modulus of elasticity, G, and Poisson's coefficients in the two directions, as well as the weight per unit area of the slab. Define template. Masonry panels. Allows you to define the masonry type elements, that is all the elements with which to build the masonry panels of the structural model. In the left list type the name of the element type you want to define. On the right side characterize the element, assigning material type and thickness. In the Define menu, Element Templates, Foundations. We see the definitions used for foundations, wall and column foundations. We now access the Plan Editor, which is one of the two simplified working environments, together with the Wall Editor, dedicated to constructing the geometric model of the building. Build, Plan Builder. From the menu Reference Lines, Import from DXF. Allows to import, in this modeling environment, 2D CAD drawings, representative of the current story plan in DXF format. To use them as reference for the import, clicking on the command opens a selection window in the current working folder, from which you can select the DXF file. Select the DXF file you want to import, define the unit of measurement and import the drawing. Use the DXF drawing to draw the geometrical model and, in particular, draw the plan lines. Choose the element type format and alignment and draw the wall, relying on the previously imported reference line. To accurately draw the plan lines, use the graphic clips. The relative position between the footprint of the plan line and the fixed line is determined by the selected alignment, which can be all left, all right or centered with respect to the drawn fixed line. After drawing the plan line, right-click and from the context menu select End or Cancel, to cancel the last point, or Escape from the keyboard to exit the command. We continue drawing the interior walls of the building. We select the format, that is the type of element in the right panel, and in the graphical environment we draw the floor line starting from the intersection with the already drawn floor line. The plan line must intersect the orthogonal line at the fixed line. The intersected wall is automatically broken. We continue with the modeling from the story editor and draw all the walls, following the previous criteria. If you go to the main program environment, you will immediately see the 3D geometric model, that is the walls you have just drawn. Getting back into the plant modeling environment, we select a wall and using the copy plan command, with the appropriate filters, we copy the selected element to the upper floor. We proceed with all the floor lines that we want to copy to the upper floor. Viewing the 3D model from the main program environment. Access the wall editor, wall builder. In this environment it is also possible to import a drawing from DXF, to use it as a layout for the correct positioning of the openings. Here are the reference lines displayed in light gray, and the wall panels previously defined at the first floor. In the construction menu, select the opening command. Using the newly imported DXF drawing, we draw the openings. The creation of the element is always finished by clicking the right mouse button and accessing the context menu under Finish. This exits the opening drawing command. Let us now see how to draw complete masonry regions from the wall modeling environment. In the construction menu, select Wall, Masonry. Select the format on the right and draw the solid region. We are drawing wall regions to which it is then possible to assign different formats, depending on the geometry of the geometric model. Click Apply Template to apply the desired formatting to the template elements. In particular, apply the desired template to the selected wall. In the Properties panel on the right, select the desired template and apply it in the Graphics area by selecting the geometric element. A template legend shows up in the upper left corner. We visualize what we have created working as a plan editor in a 3D environment. Accessing again to the wall editor, we draw the openings of the second level. From the wall editor, it is possible to access directly to the floor plan editor. And from this environment, by means of the current level command or by means of the up or down level commands, it is possible to navigate through the different floor elevations. If, as in this case, we observe a display error in the geometric model, which shows a different thickness on the previously edited wall, we will use the command update computational model. We select the walls, and once again we use the copy to other levels command. This time we also select the openings, as well as the plan lines, and with the copy only if selected option activated, we copy the selected elements to the upper level. Now we visualize the 3D model with the newly created wall. From the wall editor, view according to format. View, color according to template. Using the Apply Template command, select the template you want to apply and assign it to the wall panel by clicking on the element. Pressing the Escape key on the keyboard exits the editing command just used. Using the Wall Navigator in the upper left corner, we select Wall 3 and again use DXF to draw the openings in the selected wall. We select the DXF, set the layer and unit and import. Again, we have a trace to draw the openings and define the solid regions of the stories above the first one. From the menu, create opening. By selecting any point, it is possible to create reference lines, horizontal or vertical, that pass through that point. For example, we select a point and, from the context menu, we create a reference line for that point. We create vertical reference lines, lateral to the openings. We select a point in the opening and create the reference line using a contextual menu command. Once these reference lines have been created, proceed to draw the solid regions. Select the template, choose Other Templates and access the selection window of all templates. Create 3 full regions in the other regions for the openings. Select the desired template and draw the regions under the openings, as shown above. Now we draw the openings, using the previously imported DXF traces. We click with the right mouse button to complete the drawing operation and select the Finish command to close. Next, we will briefly show another way to draw the whole region, and then apply reinforcements or modifications in certain circumscribed areas. These are areas where you can define different thicknesses for the region or other material, or apply reinforcements. By selecting the Plan Builder command that is available in the toolbar of this environment, it is possible to switch from the Wall Builder editor to the Plan Builder or Story Plan editor. Specifically, we are at the elevation where we have just drawn the solid regions. We want to copy the wall and the openings that we have just drawn to the upper floor, using the functionality of copying elements from one floor to another. We select the wall we want to copy and click on Copy to other levels using the filters appropriately. Copy Only if selected allows you to copy only the selected elements. Then click on Copy to next level. We return to the Wall Editor through the Wall Builder command. Via the menu view, Color According to, we can decide to color the geometrical elements according to the template, element type. Let us return to the three-dimensional model. We notice that the wall thickness is not consistent with the other layers. In the Model menu, we select the Update Computational Model command. The model is updated correctly. We access again to the Walls editor, and with the Walls navigator, we select the Wall 6. With the menu reference line, we select the DXF to import to have a hint to draw also the holes of this wall. We select the DXF file, then the layer or layers we want to import and set the CAD drawing units. Then import. From the Draw menu, we select the Opening command, and using the reference lines imported from the DXF, we draw the openings. With the right mouse button, in the Context menu we select Finish to complete the operation and exit the command. Alternatively, you can press the Escape key on the keyboard to exit the drawing mode. From the Wall editor, using the Wall navigator, select Wall 5. And proceed again to introduce the openings, following the same methodology as before. We import a DXF. And we use the reference lines to draw the openings correctly. After drawing the first opening, using snaps and reference lines imported from DXF, we switch to Edit mode and select the opening we just drew. After selecting the opening, in Edit mode, we select Copy in the Edit Object panel on the right. We attach the object to a vertex and copy it using snaps and reference lines imported from DXF. Once this object copying procedure is completed, click the right mouse button, select Finish in the Context menu and exit the command. We proceed in a similar way, selecting Wall 7 in the Wall navigator. From the Reference Line menu, we import our drawing from DXF to use it as a layout to model the openings. The procedure is similar to the one seen with the previous walls. In the Draw menu, select the Opening command and draw the openings from the Wall editor. We proceed with Wall 8 and define the openings in the same way, importing the drawing with the traces of the openings from DXF. The procedure to follow is identical to the one seen before. Select the Opening command and draw the openings. When leaving the wall editing, the 3D model is updated. And now we go to the story modeling environment to start defining the slabs. We access the Plan Builder and go to the desired elevation. For example, in this case we are at elevation 340, the first floor. Select the command Rectangular Floor from the Draw menu, which allows us to model slabs with a rectangular mesh. We select the template in the texture, that is, the slab's load distribution direction, in the Properties panel on the right. By pointing with the mouse and left-clicking on two opposite points from the diagonal of the rectangle, we define the rectangular slab. We proceed similarly for all rectangular mesh slabs of the current story, and as soon as we complete the entry, with the right mouse button, from the context menu we select the Finish command to exit and complete the operation. Using the Go to Top Level command, we move from the current elevation to elevation 680. And we proceed to create the floors, defining again rectangular floor slabs. When the first floor is created, a message shows up. There are vertices where the floor lines converge at different floor heights. The program performs a check and asks the user whether he wants the mesh point of the indicated floor to be at that height or at the floor level. If the answer is no, the height of the mesh point remains at floor level. This way, we have defined the slabs with a horizontal load distribution, and to change it, we have to do the following. We switch to Edit mode, select an element, in this case a floor slab, and edit the layout, using the command available in the Edit Object panel. Using the same procedure, we edit the layout of all floors. Remember that it is also possible to select several floors and edit the layout of all the selected floors. A detail of the slab loading direction and the load percentages on each side of the mesh are shown below. By default, the option Distribute Load Proportionally to Mesh Side Length is always active. In fact, the option Proportional to Edge Length is active. If you want to customize the distribution, changing from unidirectional to custom, simply change the texture to custom and then select or deselect the mesh sides according to the load distribution. We move to the upper level, remaining in this floor modeling environment. We model the rectangular slabs in the same way as we have seen for the lower levels. We can also decide to use the option Copy Elements from one floor to another and copy the slabs already defined in the lower level. Let us use the filters for convenience, copying only the selected elements, that is the two selected slabs, and copy them to the upper floor. We switch from the floor modeling environment to the main environment, so we can take a look at the three-dimensional model. Remember that it is advisable not to perform work sessions in the floor modeling environment for too long, as all changes made to the model while operating in the floor modeling environment are not saved, and the model is not updated. When moving to the 3D model, the computational model is regenerated, and we can save the model with the changes we have made so far. Let's proceed to the loads definition. From the Define menu, Loads. In particular, we will define area loads. The load definition window, like almost all element definition windows in 3DMacro, consists of two parts. On the left is the table of elements, or loads in this case, and on the right is the table containing the load entries for each load defined on the left. Go to the free row on the left and type the name of the load, then define the load entries on the right. The first entry, gravity, cannot be modified. It reminds us that the self-weight is automatically considered and does not need to be defined within each area load type. Select the first row under own weight, and type the name of the first load item in the load item column. To the floor's load we are defining, we add a variable load entry. We type in the load item field and select the load condition via the drop-down menu. When selecting the load condition variable, the type and value fields as well as the use destination and combination coefficients are automatically filled in. The user must then select the load type from the drop-down menu, for example A1. Spaces for domestic and residential, as per National Technical Standards guidelines, and follow the standard value. The same for the use destination, according to which the combination coefficients are assigned. Let's add a new area load, roof. Going to the last row of the table on the left, we write in the table field. Each area load is automatically assigned an identifying color. We also define the variable load in this case. In this case we assign a load type H non-accessible floors. The value of the load is determined automatically and also the combination coefficients, after selecting the use destination. Click OK and close to save and exit this window. Back in the 3D environment, you can save the model. When accessing the floor modeling environment, we select all the slabs to apply the newly defined surface loads. We select all the floors with the right button and access the floor's context menu. We notice that 5 slabs have been selected, and from the context menu that opens when we click on the floor's element, we select Assign Area Loads and assign the desired load. In this case we select the area floors load. In the next step, we proceed identically to apply area loads to the slabs. We select the slabs and apply the area load from the context menu floors. Finally, at the last level, we apply the roof area load. In the View menu, we select the color command according to load to show the loads applied to the floors. For example, at level Z equals 1020 we apply the area load roof. At the Z equals 680 level, we applied the floor's area load, and also at the Z equals 340 level. In the first floor, elevation 0 to 340. We select all, that is, we select all the plan lines, and from the plan lines context menu, we create the foundation, selecting the Create/Edit Base Foundation command. Back in the main environment, we see the building with the foundation at the base. From the View, Computational Model menu, or alternatively by pressing Alt+C on the keyboard, you can view the computational model. We return to the wall modeling environment, Wall Builder, and use the Wall Navigator to scroll through the walls until the desired wall is displayed. In the Construction menu, we select the Mesh Divide Line command, which is used to create dividing lines in the base mesh. In fact, the base mesh is automatically created according to the position of the openings, as can be seen in the wall selected here. The insertion of dividing lines in the mesh serves to further refine the discretization into macro elements. Currently we exit the command and return first to the geometric view, using the View, Computational Model command, or Alt+C on the keyboard. If we are in the computational view, in fact, this command returns us to the geometric model view. Then, using the Mesh Divide Line command, we draw a dividing line of the mesh to equalize the discretization of the macro elements between one opening and the next. We draw a horizontal or vertical line. If the drawn line is oblique, the program indicates that it is impossible to draw a mesh dividing line. This control is necessary to avoid generating non-rectangular macro elements. We draw 3 division lines of the mesh in the 3 levels. By right-clicking the mouse, we access the context menu and exit the command with Finish or Cancel. Visualizing the computational model, we see that the central macro elements have been divided and the mesh is more homogeneous. We scroll through all the walls using the Wall Navigator to check the mesh. Let's go back to the main model and, in particular, to the visualization of the geometric model. And let's perform the pushover analysis.